Okay, so basically when you're talking to your cell phone, so your voice, that is a sound wave, they go to microphone, they converting into electrical. And that will be analog signal. Okay, and that analog signal will be go to the device we call an encoder. Okay, you can see here, supposed to be your voice here. Okay, when they go to the microphone, they convert into analog. Okay, and then they go to the encoder. That's what analog to digital converter. You understand is your cell phone, basically inside, they will be like a small computer. Okay, and they will be go to CPU. That for the long time. Now they using the other device. They call a microcontroller. But that will be working with the binary. So that's why they need to converting from AD converter to the binary. So go into the controller here, whatever they want to do. And when they sending out from the computer send it out, they must be in binary. Okay, and but that binary will be go to the device we call a decoder, and that will be digital to analog converter. Okay, and finally your voice will be here. That's how the process in any system is supposed to be doing the same way. Okay, most real world information that will be analog, like your voice, temperature, vibration, whatever, they will be analog. Like they say speed, weight, pressure, light intensity, and position measurement are all analog in nature. The following show digital system with analog input and analog output. Your voice coming in and your voice coming out. Okay. The analog input voltage could be produced by what we call a transducer. A transducer is defined as a device that converting one form of energy to another. For instance, a photocell could be used as an input transducer to give a voltage proportional to light intensity. Light energy is being converted into electrical energy by the photocell. Another transducer may include microphone, speaker, temperature, and so on. Okay, now, first thing, we go with the DAC converter. If you're looking on this circuitry here, you know, there's a 4-bit binary counter. Okay, when you apply the clock, they will be counting from 0 to 15. Okay, and that binary will be connected to the device we call a DA converter with a resolution is 1 volt. So if you're looking the output with the oscilloscope, you can see this signal. Okay, now first thing, counter at the 0, 0, 0, 0, output 0 volt. Counter go to number 1, output go to 1 volt, keep going. See that? Until 1, 1, 1, 1, 15. So that is right here. Okay, so basically the resolution is 1 volt. So that's why when you go up to 15, you get 15 volt maximum. And what happened here? That means the counter now go back to 0. And they keep going again. Okay? So that's what they call an output waveform of the DA converter. That the input are provided by binary counter. So the solution is 1 volt. So when you're going from binary 0 to 1, and they go 1 volt, and they go 2 volt, and go on. Okay? In here, the top right here, they call it F. That means full scale. Okay? And now, for each one here, see that? How many? If you count, you can see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and 15. Okay, let's see. Okay, what we call a step size. Okay, and a number of steps. How many number of steps?
$16.
Okay, let's see. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Okay, and the last one here will be 50. Okay, and how many voltage for 1 step? That means from here going to here, that's the step size. How many volt?
1 volt.
1 volt. Okay. The question is, if I want the output 0.5 volt, can we do it? I said if I want output to be 0.5 volt for this DA converter, can we do it or not? First thing you have to know, we cannot get the output 0.5 volt. The reason is, each time you go to one step, they go by 1 volt. That means the first thing you get a 0, 0, 0, 0. They get 0 volt. However, when they count 0, 0, 0, 1, they get 1 volt. That means you cannot get 0.5 volt. If you want it to get output 0.5 volt, what can we do? What I can tell you, get another DA, okay, with resolution. Zero point 5 volt. If you try to get a smaller step, for each step size, you have to change the converter. You cannot do anything in order to get the answer for different DA converter. Each DA converter, they already telling you the resolution. Okay. More small got higher. Now, this picture given to you a little more. First thing you see, that is the input here, binary, A0 to A7, 8-bit DA converter. That's what we'll be working in the lab, okay? And this binary here go into DA converter. They will be converting into either voltage output or current output, okay? And this picture will be given for you to see what the pin number, okay? What the input or what the output, and what else will be explained to you for the next one. But one very popular and inexpensive 8-bit DA converter that will be DAC 08. Okay. Different company get a minor difference. However, they still 8-bit. Now you can see this is DA converter. 4-bit. However, the different the resolution will be different. If you're looking on the display with the binary D0, 1, 2, 3, what the voltage full scale? The full scale, that means when the binary go to the maximum, right here. 1, 1, 1, 1, and you get 9.375 volt. That's the full scale. And then, what the step size? What the value of the step size? The value of the step size when you change the binary 1 bit, whatever the voltage change, they will step size. For example, in here, you're going from 0 to 1, and the step size change 0.625. That's your step size. Okay. The thing is that only thing we need. Last time we already showed you 4-bit DA converter. Step size is 1 volt. Okay. And now the same 4-bit. However, step size will be 0.675 volt. Okay, resolution. Resolution of the DA converter is defined as the smallest change that can occur in analog output as a result of a change in the digital input. So percent of resolution equals step size divided to the full scale times 100%. Okay. Reciprocal of the number of discrete steps in the output. For instance, 4-bit DA converter had 15 steps. Okay, that means number of steps. The resolution is the formula 1 divided to power of 4. 4 means 4-bit minus 1 times 100, that given you 6.67%. That is the way to calculate the resolution of the DA converter. Okay. And the total number of steps using the formula 2 power of n minus 1. For example, you get n equal 4 bit. 2 power 4, 16 minus 1. You get number of step is 50. Okay, let's see. Example. They want to determine the resolution of an 8-bit, okay, and a 12-bit. DA converter in terms of percent. So, answer for 8-bit, what you get? Resolution. This is the formula. 1 divide okay, 2 power of 8 minus 1 times 100%. So what you get? 2 power of 8 will be 256 minus 1 to 55. So 1 divide 255 equal, okay, and 2 times 100. What you get? Okay, who tell me the answer for A?
.39, Mr. Farm.
Okay. %39, right?
Right.
Okay, what happened to B?
DA can determine.
Okay, the formula will be 1 2 power of 12 minus 1 times 100%.
0.02%. 2524.
So your answer will be 0.02.
Yes.
Okay, who else?
Let me see.
Anyone get the same 0.02?
That's correct.
Yeah, 0.0244. That's the correct answer. The next one, a 5-bit DA converter. They given to you V out 0.2 volt for the binary 001. The question is, what the V out for the binary 111? That means full scale. Okay. How can we do? Okay, for the input 11111. I want to know total number of step size of the DA converter. How many number? You can say this is the formula to calculate the step. Okay, how many number step? And it applies to the
33.
example number 2.
31.
Yeah, exactly. 2 power 5.
31. Mhm.
You get 31 step. Now, each step will be how many volts?
0.2 volts.
0.2.
0.2 volt, right?
Right.
And
Mhm.
you get the 31 step, you take 31 half 0.2. That given you 6.2 volt.
Two. Four. Mhm.
Okay, that is the minimum thing you need to know about DA converter. That means the formula how to calculate the resolution. The second thing you need to know how many number of steps, okay, of that DA converter. Okay, try to this one, see how many students can get through it. A 10-bit DA converter has a step size of 10 millivolt. They want to determine the full scale output voltage and the percentage of resolution. Do it and tell me your calculation. Make sure you try to do it. Even you can get or you cannot get it.
The output scale is the 10.23 volts.
Full scale, how many volt? 10 point?
10.23 volts.
Okay.
23.
Perfect. Perfect. That's what I get. Okay. And then percent of resolution. The formula will be 1 over 2 power of 10 minus 1 times 100%.
0.01, almost 0.1.
Yeah, you round up 0.1. However, this one not supposed to be rounded up. The thing is they deal with the accuracy 0.97.
0.09. Mhm. Okay.
That means each step size will be equal 0.07 milli. Step size equal 10 millivolt. Okay. Now this is the circuitry will be in the lab. So basically, we don't care what's going on inside here. If you want, go to university, take the course they design IC. That means they will be teach you how to design inside here. Okay. However, for us, just for application, how that device working. Okay. Now, if you're looking on this device, they get total pin number will be 16. Okay. And the first thing you can see pin 13 will be connected to 15 volt. This I see from my Motorola. So that's a minor difference from the one in the lab. The one in the lab, they connect 13 equal 15 volt or 12 volt. And pin number 3 will be connected to minus 12 volt. Okay. And then whatever connection, you should be follow that. When I talking about the lab 12, if you understand this circuitry here, will be have no problem for the lab number 12. First thing you can see right here, they get a 10 volt. And this is a 5 kilo ohm. This current they call I reference. Okay, I reference, how do we know? You take 10 volt divide 5K, you get 2 milliamp. And if you're looking at the output here, I out, they're telling you they're using the reference, I reference, to get the current I out. That means the current I out cannot be higher than 2 milliamp. Okay, that is when you try to get 2 milliamp here. Okay, so do not try to measure the current anyway. Okay, the thing is basically in the lab you can do. However, in the side of the company, you cannot measure. The thing is when you want to measure the current, you have to break the wire. Okay, using a DMM to measure the current. That cannot happen. So my question is, you're supposed to get 2 milliamp in here. So if you measure pin 14 voltage, what do you think you get? The thing is sometimes your circuitry not working. That's why you have to troubleshoot it. Okay? So I said you using meter, measure the voltage at pin 14. What do you think the voltage you're supposed to get? Who knows? I give you an example. If I measure at this point, I get 10 volts. You think it's a right or wrong?
Right.
That's a very simple question. If you measure pin 14, you get 10 volts. You think they right or it's wrong?
8 volt, I'm sorry.
The answer will be right or wrong. Okay, I can tell you. They have to be wrong. Why do I know that is wrong?
5K resistor.
No, we're not talking about the resistor. Supposed to be 5K. But when you measure at pin 14, you get 10 volts. And my question is it a right or wrong? And I already telling you that will be wrong. Who can explain to me why it's wrong?
Because in the past, Mr. Pham, when you talked about this particular IC, you stated that the manufacturer manufactured it a certain way, and pin 14 should be 0. And if it measures anything other than 0, the IC needs to be replaced. 2 milliamps times 5K is 10 volts, but for this particular IC and the way it's manufactured, that won't be the case if you measure on pin 14. You should get 0 volts.
You're right. However, I need to explain to you. If you get a 10 volt on here, You get a 10 volt here, you get a 10 volt here. What the current?
Zero.
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 However, the requirement will be 2 milliamp. That's why I say 10 volt divide 5K, you get 2 milliamp. So basically, when you measure at this point, you suppose to get 0 volt. That 0 volt happen inside the converter. They get too many circuitry inside transistor. They connect it to ground. So that's why you're able to get 2 milliamp.
A quick question, Mr. Pham.
Yeah,
Okay, on both sides, once again, on both sides of the resistor, you would, one side you have 10, the other side you have 10, so 10 minus 10 is 0, but you have to have 2 milliamps there. Is that what you're saying?
yeah, you asking for 2 milliamp.
Mm-hmm.
So if pin 14, you get 10 volt, means you get 0 amp, right?
Right,
No current.
right.
In order to get 2 milliamp, pin 14 must be round.
Mm-hmm. Okay, and as I was saying earlier, so all of that takes place inside of this IC.
Exactly.
And anytime for this IC, if you can't get pin 14 to be 0, then the IC needs to be replaced.
Exactly.
Okay.
Well, there's a voltage regulator there at 10 volts, isn't there?
Yeah, that will be applied 10 volt.
Right, so you
Yeah,
technically,
then when we using the lab, you can see how can we get 10.
right, so technically, the 5K is gonna drop it to 0. But if you have backfeed from pin 14, your voltage regulator is probably fried, right?
You
Voltage-
suppose pin 14 have to be 0, right?
Right, that's what I'm saying, but your voltage regulator, if it's not working, like
What you mean, the voltage
like Joe,
regulator?
it's like Joe was saying, right? It's supposed to be measured 0 at 14.
And you must get 10 volt on the other side of the resistor.
And if the voltage regulator fails
What the voltage regulator? You're talking about 10 volt?
for 10 volts, correct? If the voltage,
Okay.
right?
If you want it, that means first thing they already telling you, verify 10 volt on one side of the 5 kilo ohm.
So
Before
one
you
side's gotta-
measure pin 14,
So one side's got to be 0 volts and the other side's got to be 10 volts.
exactly. What I tried to explain to you, first thing they want to make sure you get 10 volt here before you can measure pin 14. Otherwise, you get 2 unknown.
Will that resistor bias voltage from pin 14 so that it won't be 0? So it'd be like maybe 1 volt or 2 volts. Well,
And
pin
now-
4 can't, never will. Even if a voltage regulator was there, will the resistor bias voltage from the IC if it was grounded?
Which one is that?
10 volts.
You're talking about pin 14?
If on the 10 volt side it was grounded and the 5K resistor was there,
Okay,
Would-
you're talking about this one.
right? Would the 5K bias voltage from 14 to the circuit voltage that the IC is working at, will it bias 5 volts? Can it bias 5 volts or 2 volts? Can it bias any voltage if that side was grounded?
Okay, If you want 10 volt, now they can be 5 volt.
The only question is if the 10-volt side was grounded, will that resistor bias any amount of voltage from pin 14? Meaning that's telling you that you're not going to have 0 volts. You can't have 0 volts. I'm just
Okay, they must get 0. The thing is inside here, they not try to adjust any voltage here. They just short it to round if they working. If you don't want 5K, you can change the other resistor. However, the key point is you changing to 2.5K. Then you have to change this guy in order to divide to get 2 milliamp. They reference it to milliamp. Only thing that you make sure you get the reference is to milliamp. They don't have to be 5 kilo ohm. You can change it to 10 kilo ohm. However, if you change 10 kilo ohm, then you have to change the reference right here. Go up to 20 volt. You divide to 10K, you get 2 milliamp. That's what they want. They want 2 milliamp for this IC.
But Mr. Farm,
Yeah,
if the voltage reference equals 0 volt, so the
Okay,
pin
now-
14 will be
cannot.
0,
cannot
Cannot.
0.
or there has to be some voltage.
Right, the thing that they want 2
Oh,
milliamp.
because the curve. Yeah, I know. Oh, okay. Makes sense.
They want 2 milliamp. If you're using 10, have to be 5K. If you got use 20 volt, have to be 10K. That means you divide that, make sure you get 2 milliamp. That's the reference current for this type of DA converter.
And Mr. Pham, you're also talking about, so they'll know, is like when you do this circuit, sometimes you might not get that 5K resistor just exactly. So you have to adjust your voltage in accordance with the size of the resistor you have.
Exactly. If you get 4.5K, then you have to say which voltage divide to 4.5K to get 2 milliamp.
Right, the key is 2 milliamps.
Exactly, that's a reference for this DA converter.
Hey, Mr. Pham, one last thing. I guess this was for everybody. I'm pretty sure I heard you say this right. When you're out in industry, well, here in the class, in the lab, you are allowed to break the circuit to measure current. But when you're out in industry uses these automation machines to make the circuits. So you can't break the circuit. You have to measure the voltage.
Exactly.
All right.
They're not allow you to measure the current.
Right. Everything, when you're out in the field in industry, you measure voltage. You don't measure current.
Exactly. Except the circuitry already designed for you to measure the current.
Right.
So it's like in lab volt. You see that?
Yeah.
When you're working on the DC fundamental,
Right.
you can measure the current, the thing is, they already prepare.
It's engineered to do that.
Right.
But if you like I said, even on like these breadboards we're building, we can break because we're putting the wires in, we can break the circuit and measure the current.
Right.
But if we're at a company, the boss, the manager would be mad if you broke the circuit to measure the current.
You get a layoff right away. The basic thing you still don't know. The thing is when you break the wire, then the problem is They don't know who you can fix the circuit board or not, but you break it, that means you damage the circuit board. That's not allowed. Okay, now, next question. Who now tell me this circuitry here? What is the name of this circuit?
That's not the sample and hold, is it?
An
No.
inverting amplifier.
No.
50-50, Mr. Pham, current controller circuit.
Hey, man. What in here?
That's current.
Current. What here?
That's analog voltage.
So the device name will be current. To voltage. Converter.
Okay.
That means current coming in, output coming out, voltage coming out. Even you see 741 just op amp. However, depending on application, they can be follower, they can be inverting amplifier, non-inverting, summing, too many things. And this circuitry, basically, the name will be current to voltage converter.
And-
Input is current, output is voltage. Yeah,
But but also too, that the op amping, because of that feedback resistor, that's inverting, right?
no, op amp just general.
Yeah, okay. I know, but you got an op amp, you got a feedback resistor, and you got the plus going to ground. Isn't that like sort of like inverting or something?
Converter, that inverting amplifier.
Okay,
Right.
all right, okay, yeah.
But in this, not a voltage at the input. Okay? So that's why they get a special name, current to voltage converter, converting from a current to the voltage. Okay? And easy to recognize output here is equal the current time resistor.
So
Okay?
you should get an analog voltage there.
Exactly. So that's why they say analog Vout will going from 0 to maximum 10 volt. Okay, and this is the formula. Okay, in order to calculate the voltage. Will be in more detail when I talking about the lab, number 12. This, they just using two binary. Okay, they counting from 0 up to 255, and they connect this circuitry to analog scope, and you looking into analog scope, you can see the signal look like. Okay, they will be too small step size, so cannot see it. Up here, that full scale, and counter back 0. They go back 0, and they keep counting. Okay. Okay, so this will be A to D converter. You understand A to D? That means analog coming in, binary coming out. This is a block diagram inside AD converter. You can see input right here, analog voltage. Output in here, binary. Output, that's what they call AD converter. Okay? Now, try to see in the circuitry how many things we know. This basically just a switch. Put it out, they connect to the route. Okay? This is counter. 8-bit. So 8-bit they counting from 0 to 55. Okay? This counter we already learned. You understand the clear input, active low. That means when you press this down, they clear the output to be 0. Okay? If you get a question, just stop me, let me know. And now, this is the clock input, okay? And they go to the AND gate and go to the counter. If you get a clock, counter will be counting. And this circuitry here, who know what the name? What are the name of this part in here? This is a comparator. Okay? How the comparator working?
It compares the voltage on the plus to the voltage on the minus.
Exactly. They compare between the input at positive to input at negative. If a input positive higher than negative, output will be at logic 1. If a negative input higher than the positive, output will be 0. That's a very simple comparator. Normally, we learn in analog, they compare positive to negative, and output will be go to saturation voltage. However, this design using in the digital circuitry, so they not go to the saturation. Output, they go to logic 1 or 0.
Hey, Mr.
Okay.
Sam, can you write that little note, that 1 and 0, how you
Okay.
get, can you write that on the side?
Okay. If I say if positive, okay, greater than, okay, output logic 1. If input positive, less than output
Okay, yeah, thanks a lot. That kind of helps you.
Okay, you're welcome.
Mhm.
The thing is when you're looking into the circuitry, I don't care what, but it's a divide in the circuitry. You have to understand what is it, how they work it. Again, I already explained to you. This will be faded out, output will be 0, clear, output counter. And the counter here only will be counting if the clock go into here. Okay? This is clock go into one side of the AND gate. If you get logic 1 here, then you get a clock. If you get a 0 here, no clock, you stop the counter. Okay, next one. Tell me what is it here? You know that will be a D. Deluxe. Okay. 1. Let's see. 73. 373. In your lab, you already using this one on the memory. What that deluxe? Who knows?
Oh, you mean on the DLATS? Yeah, it holds the information or data at the beginning until the IC is latched.
So it means the input equal the output.
That means in here, okay, they using the clock.
On the clock pulse.
So basically, we cannot be last.
Oh, okay.
Okay.
That will be X trigger,
Oh, so that's like the 374 then,
right?
because one's
The
3.
flip-flop, and will be 74. Also in the lab 11. They need a clock. So the data at the input here can go inside.
Oh,
Okay. Then
Right.
can we go into the output?
Right. That's correct.
So if you see in the picture, they telling you this analog voltage, your voice, whatever here. I can give it you example. 3 volt. So they will be converting 3 volt to binary. That's what device we call a to D converter. Okay, now I show you how they work. Last one. This one we just go through it. DA converter. That means this is the binary. Okay? This is the binary. And this is analog coming out. So my question is, at the beginning, you press to clear. So output here will be 0. On 0, right?
Right.
So they go into the input of DA converter. What voltage here? V out. Right?
Right. 0.
0.
0 in, 0 out.
So 0 here, that means you get a 0 here. And this is 3 volt.
So,
What logic at the output of the comparator?
1.
one.
But
Mhm.
that one allowed to the clock
To go to count.
go here.
Right.
Mhm.
Okay?
Mm.
And the counter will be stuck counting. Okay?
Mhm.
They can be counting 0 up to 255, right?
And it'll keep on counting until it gets to the point where the that minus sign is greater than the
Positive.
plus sign.
Okay. They will be counting. Okay. I say up to 3.1 volt. Okay.
Right.
So 3.1 volt, now higher than 3. This coming to be
0.
0.
And the clock stops.
No more clock.
Mm.
Whatever binary coming here, you can see this is 0 here, go to the clock here. So they go 0 to 1. Okay. They will be 1 to 0, negative clock. So that's why they loading that binary to the output of the D flip-flop. So this is the binary.
Hey, Mr. Pham, and the D flip-flop is a positive clock, right?
They're depending on. They can be negative, they can be positive. Depend on the IC. They don't have to. However, when you analyze, they're not telling you what the path for the D. However, they put a negative clock, and you follow negative clock.
Mm.
So basically, when at this point here, they going from 1 to 0. That means they loading whatever binary here to the output here. That's how A to D inside the circuitry, the IC, they work it. Okay, in here they given you AD, ADC 804. Okay, this just the IC. If you want information, then you can go Google, typing ADC 804. They given you all of the information.
Hey, Mr. Pham, I know you're in a hurry. Real quickly, can you just explain like pin 1? No, that one you was on, right there. You know, like chip select and pin 1, 2, and 3.
You're talking about pin number 1,
Right.
chip select. You understand the chip select normally active low. That means if it's low, this IC will be working. If it's high, look like this IC not there,
It's not working if it's high?
right? The thing is basically, if you're looking at in here, DB, that means they will be connected into the data system in the computer. You understand me? In the computer, you get 8-bit data. That means all of the IC in the computer can share the same at 8-bit. If a 16-bit, that means all of the IC in the computer will be share the same 16-bit or 32-bit. So basically, on that data line in the computer, only one IC allowed to work. So chip select, that only telling you pin number 1 is 0. Then this IC can send the data, okay, to the data bus of the computer. If chip select equal 1, look like this IC not there. So they can not load it current on the data bus.
Okay.
And in order to control, we already learned. I already telling you. This IC here. You know this one, right? What's the name?
Oh, NAND.
What is the name of this IC?
Oh, man. Help, somebody help.
Hey,
You might as well just go ahead and tell us, Mr. Pham. Oh, the decoder. Where one IC, well, oh, 1 0 at a time.
right. Only one output 0.
Yeah, that's right.
So that's
Yeah.
why decoder is into control on of the IC.
Mhm,
Okay, when they tie the output together,
mhm.
they allow only one IC connect to the data bus to be on.
Mhm. All right, thank you, Mr. Pham.
You're welcome. How come you guys can let me memorize for you guys? Okay, so basically, if you're looking on that one, they just wiring diagram for the circuitry, that ADC. This is our ADC here. Okay, that means they apply voltage, okay, to the analog input, and this is the binary coming out. Okay, so basically, if you go to the column, then they can give you this type of the lab. However, in this program, we're using automatically. That means binary coming in and the computer will be reading output. You get an analog coming, binary coming out. We're using computer reading that one, analyze, telling you right or wrong. So you don't have to connect to the LED to see which LED on or which one will be off. That's it. Okay, so basically that will be DA converter and AD converter.
So like on those big, like on the bigger circuits you have us do, like near the end of the semester, you have digital to analog, and then you go back analog to digital.
Exactly.
Yeah, okay, got you.
Instead you connect to LED to see which LED on or which is off.
Right, got you.
Okay, but we're using automatic. We're reading binary here and telling you they right or wrong.
Mhm.
Okay,
That's why you have those 8 lights inside the controller box.
right.
This is only analog to digital though, right?
That analog to digital.
Right.
Okay, now let me quickly share for you for the lab 12. The lab 12 very simple. Okay, if you're looking on that one here, 1, 2, 3, 4, 5, 6 IC. One, 2, you already know. Binary counter 191. The way they connect this way, that means the counter will be counting 0 to 255. Okay? And also, you can loading any number you want, any number you choose, and they go to U3 to verify. That's easy. Okay? Then this binary output of the counter connect to D to A converter. This D to A converter, they will be using 2 milliamp reference. Go to pin 14 here. So pin number 1 will be connected to the port, connect to 12 volt. So the first thing what they telling you, connect the meter to pin number 1 of unit 6, then adjust the ports until pin number 1 is 10 volt. That's what we're using 10. Okay? Adjust connect to pin number 3. Adjust the port in here until pin number 3 equal 10. So you get a 10 volt here. If they rounded pin 14 inside, you get 2 milliamp. Okay? And pin number 3 connect to minus 12 volt. And you get a capacitor. One side connect to minus 12. Another side connect to pin 16. Okay? And pin number 3 connect to 12 volt. And then you get the op-amp 741. For op-amp 741, pin 7 connect to 12 volt. Pin number 4 minus 12 volt. So I have to be very, very careful. Okay? The thing is inside circuitry, you get 5 volt, you get 12 volt, you get minus 12. If they tie together, they cook your board right away. So in here, you can see the port, we don't care about the port ABC, just a reference. However, this is the one you have to do. So you have to enter here. I given you example. For that for input AA, and that will be 1, 0, 1, 0, 1. Zero. One, 0. Now, this is I already do for you. The converting binary to the decimal. That will be 170. And now the height, you know the height, right? 0 height. And now we need to calculate the DAC current. Take the decimal times 2 milliamp divide 256. So you can say equal what? Decimal. That means this guy. Okay? Time. Two divide 256. So that is what you get the current. And now you want the voltage, you take V out time the current times 5K. So let's see. I can say equal this current here. Okay. Time. No. No. Let's Let's see, which one is it? Here, time 5. Okay, I'm wrong right here. Okay, so basically, there, time,
So was that supposed to be like
time,
2 milliamps times 170?
yeah,
And then you divide by 256.
right. No. No. Let's see, which one is it here? Okay,
That's more.
that will be 6.64 volt. Okay, so you have to complete that guy.
Oh, yeah, you get the current, which is 1.328 milliamps, and then you multiply it times 5K.
Okay,
Is that right?
exactly. So, easy way to do. I can give you full scale. Okay, 1, 1, 1, 1. Okay, so now if you want to see what's going on, copy that, paste them out here. See that? Data here supposed to be F full scale. And they given you that quantity. Let's see, 255, okay, and 9.96 volt. Okay, now I already given to you the sample 10. Let's see. Just a minute. Okay, you can see that on the website. Okay, at the beginning here, I already get start step number 1, 2, 3, 4. Okay, and now you get the counting. I given you the function you have to do. Only thing we want to talking about this part here. First thing, when you run it, they're telling you connect DMM high to U6 pin 3, DMM low to ground, set DMM to measure DC, adjust 2K ports until DMM reach 10 volt, plus or minus 10%. Okay, if something fails, make sure you check U6 or 2K port. After you're done, now you go to the next. First one will be testing for first one. That means you want the output to be 6.64. You see that? The first one, that output you want 6.64. Okay, so expect value, tolerance, I gave it to you. Unit VDC, peak off type of measure VDC. Connect high, U5 pin 6, connect low, ground. Then I have to load in data AA. Okay? The thing that you understand, hack data AA. And also, I write to port B0 for loaded. Then you call the function DMF. And they will be telling you what to do. Then they tell you pass or fail. However, this is, you see the difference. A test fail, not D. Analog. So when they fail, they give it to you what they measure. Then when you go to the test number 2 for input 55, okay, and then keep going. Next one, FF and so on, 15 more tests, okay? If someone using an array, that's okay to me. But I'm not expect that. I expect you do test by test, okay? On this one, you get only one function definition, but you must be modified. So they're working with the circuitry. That is the best I can help you.
For right now, right?
Very easy, not hard to do. Only thing you want to do or not. Okay, any question, anything? If it's not, see you next week.
All right, thank you, Mr. Pham. Have a
Yeah,
good night.
good night. Good night, everyone.
Good night.
Good night.